Hi, everyone. Thank you for joining us for the NVM Express Compliance and Interoperability webinar, testing UNH-IOL guidelines and Marvell and Xinnor use cases webinar. We'll get started in just a few moments. Hi, everyone. Thank you again for joining us for NVM Express Compliance and Interoperability Testing, UNH-IOL Guidelines, and Marvell and Xinnor Use Cases webinar. I'd like to take a moment here to introduce you to our speakers. Today from the UNH-IOL, we have Carter Snay. From Marvell, we have Jeff Yuan. And from Xinnor, we have Dmitry Lifshitz. With that, I'll go ahead and hand it off to Carter to kick off the webinar.
Thank you, Nolan. All right. Hey, everybody, thank you for joining. Let's see. So hop over to the agenda. So first of all, I'll be giving an overview of the UNH-IOL, and I work with the NVMe Interop and Compliance Working Group. And then I'll be handing it off to Jeff and Dmitry to dive into use cases from Marvell and Xinnor to show how compliance testing impacts real products. So briefly about the UNH-IOL, the organization that I work for. We are an independent test lab that's been testing data communication products and networks since 1988, when we were just a single group of UNH professors trying to debug some Ethernet issues. Now we are a multi-test program lab and work directly with UNH professors and students to perform research and independent third-party testing. But jumping to what we actually do with NVM Express, we've partnered with NVM Express to create compliance and interoperability test plans and software to establish requirements to have devices and implementations published on the NVMe integrators list. So that's how UNH-IOL and NVMe work together at a high level. Let's jump into some more of the specifics about the test program, the reason we're all here. So since we're all here to learn about NVM compliance, did we lose the, there we go. All right. Since we're all here to learn about NVM Express Compliance Program and how it works and how the tests are defined and who performs the testing, let's jump in. So as I mentioned before, the UNH-IOL partners with the NVM Express organization to develop test plans, such as the one shown on screen, although there are many more available. We operate within the Interop and Compliance Workgroup within the NVM Express organization. And this is the working group that plans out the timelines of the test plans and how we actually develop them, doing the plug test planning, and also handles any compliance disputes or waivers if necessary if they arise. So for the actual process, there are two major test plan updates each year, and that takes into account the previous 6 months of new features and their associated requirements, which is really looking for the shalls and musts within the new specifications and updates. This work is done within the NVM, within the Interop and Compliance Committee, and then is presented to the wider NVMe technical workgroup for review, just like any other technical proposal or new feature is done for NVMe. For each revision of the test plans, all the new tests are FYI, meaning they are not required to pass to be eligible for a compliance and integrators list listing. This is to ensure that the new test procedures that are brand new and the new scripts and devices are all in agreement before we move the test requirement to be mandatory to become a strict requirement. So we don't want to accidentally have new test cases be overly strict if they are just new and there's an actual hardware to test against, and we're waiting for implementations to come out. So I'm going to jump ahead a little bit. Okay. So looking at the test plans, there's really 4 primary groups or categories of testing that are performed. So obviously the first one is functional tests, so making sure the new feature does what it's supposed to do. That's pretty straightforward. Then on the other side of the coin, there's error injections, so making sure that the device responds correctly when we purposely send bad commands and broken packets. There's interoperability testing to verify that the device works in multi-vendor environments with no hiccups. So in those types of tests, we're doing lots of reboots and kind of stress testing the device and making sure that it always performs as expected, regardless of the CPU complex or motherboard or any of the other types of operating systems we might be experiencing testing with. And then the fourth is the transport testing, which is really doing all the above across multiple transports. Right now, primarily the biggest one we're doing PCIe, but also Rocky, TCP, and fiber channel testing as well. So this slide really just summarizes the process that I've just described, but also adds the actual process of getting put onto the NVMe integrators list via the third-party testing at the UNH-IOL, which is when we test the device and debug with member companies if there are failures that block any sort of certification. We'll work to debug all the failures. Even if they are FYI or mandatory, we work to make sure that the failures are understood. But obviously, the mandatory failures are priority number one because those will be what might prevent listing on the integrators list. So as I said, we write the test cases, we put the test cases in the hardware or in the software. We work with member companies to send their samples to our facility, and we test them at our facility, and we work with the test engineers both on our side and the member company side until we can find a common ground and solution that actually has the device passing all the requirements that have been created by the Interop and Compliance group. So I also want to highlight that there are two lists available for being listed upon passing the required testing. So on the left side, there's the NVMe integrators list, which is really the source of truth or the main list associated with the ICC testing. But member companies can also opt to have their device listed on the main NVMe website on the compliance list on that side, which has more room for more marketing materials and additional information. Like, for example, you can have images, which is not available on the NVMe integrators list. So it's also directly on the NVMe website, which is definitely a plus. So it's another place to have the device listed after passing the testing for the NVMe integrators list. Passing the testing on the NVMe integrators list is a prerequisite to being put on the compliance list. And to highlight the software that UNH-IOL produces based on the test plans we write, this software is called IOL Interact, and it automates all the test cases that we write in the compliance test plan. And as you can see, we've had 1,500 plus test cases developed, so being able to automate those is really important. We've made modifications with member company feedback and continue to evolve the test cases and test plans as we get more feedback from member companies. So this is it's going back over 13 years. And it has feedback from all the member companies from before and previous developers, so standing on the shoulders of giants there. And this software can be run on any Linux host, and it's the software we use for both sending out to member companies as well as what we use for integrators list testing here at the UNH-IOL. And hammering it home again one last time for the member company process. In order to be put on the integrators list, you join NVMe. Then you work with the UNH-IOL to get the IOL Interact software and perform pre-testing at your own facility. And you can communicate with our test engineers to debug any issues you might find. And then you can get a scheduled reservation at the UNH-IOL lab, where we provide a test report. And if passing, the device can then be listed on the NVMe integrators list. So that's really the process in a nutshell. So now I've discussed just the compliance and interoperability testing, I'll pass it off to Marvell to go over the more real-world use cases.
Hey, you can hear me, right? Hi, this is Feng from Marvell. GF cannot make it right now. Just a very basic introduction of our group. We are NVMe hardware design and validation team. So our main focus using the IOL software is try to validate the NVMe hardware design, both for pre-silicon and post-silicon time. And we're especially focused on the hardware features, in the NVMe's, like a reset case, a PCI reset case, CRAG, and stuff like that. So it's very hardware-focused components instead of software. So that's our design. That's how we use this tool. Next slide. Yeah. So let me go through first couple slides and the details case I will let Rich, my team to present. As I said before, we leverage this automated NVMe and PCIe-based conformance test suite across both FPGA as pre-silicon and post-silicon and to accelerate complete validation. The test suite provide highly effective for critical feature validation during pre-silicon and post-silicon phases. enable us to do early bug detection and ensuring compliance alignment. So the key validation area we have here is NVMe spec-based compliance testing, PCIe spec-based compliance testing. The last one is NVMe error detection and handling. Next slide. Let me go to the next slide. Yeah, so this is pretty much our setup. We have our NVMe controller in evaluation board form factor, and we plug into a motherboard, PC or server motherboard, and then we're running the IOL software from Linux system, from host, and go through the PCI interface. So let me, Rishi, are you there?
Hi, Feng. Yeah.
Or let Rich go through the couple cases we highlighted here. How do we use the software for validation, for hardware validation? Go ahead, Rich.
So hi. So yeah, the first scenario is for checking the error handling for queue creation, which is very critical for NVMe, right? So the scenario is the queue creation should be reliable under different conditions, including like different edge cases. So if that doesn't work properly, the problem which we would observe, the problems which would cause this is like invalid completion queue IDs, unknown interrupt values, and inconsistent queue deletion sequences. So if they do happen, then we'll have unexpected queue hangs. The operations get stuck and they don't complete. We have missed completions if there's something wrong with interrupts, and unresponsive IO paths, or the worst case, data corruption or the host itself resets. Right. So the role of the compliance testing, it helped us regularly validate different scenarios, including illegal sizes, IDs, and sequences. We were able to identify multiple failures with CQID validity and queue dependencies, response codes. Due to this, we were able to implement a much more robust queue lifecycle tracking and much more stricter adherence to NVMe specifications. And we were able to have this behavior across, different OS NVMe drivers. So this was the first scenario. Moving on to the next one. So this is, as Feng had told, about the key registers, the main registers, the capabilities, the configuration, and the controller status registers. So they must strictly adhere to the NVMe spec. If the registers are not compliant, then we might have like a very inconsistent controller behavior, or rejecting valid host configurations. So that will result in us not being able to integrate with the host properly. And the impact, as we can see, host driver failures, queue initialization errors, undetected fatal errors, worst case again. So with UNH-IOL tool, we were able to validate all the critical register fields and transitions, including the capabilities, controller configuration, the interrupts, the controller status, and others. We were able to detect the specification violations early, before OS or customer level validation. So due to which we had a predictable and stable register behavior across different hosts. So the next is like PCIe transport confirmations. So the controller must support different reset actions for the PCIe PCIe hot reset, function level reset. So each reset type requires a proper hardware support, and validation is required to ensure correct controller behavior, under reset conditions. So the fallout or the impact of this is, the device is not recognized as a PCIe device after reset, or it's recognized as PCIe but not as an NVMe block, and admin or IO command timeouts post reset. So with the IOL tests, we're able to improve the silicon handling of the hot reset, functional reset, and subsystem reset. We are able to ensure a much more reliable device recovery and enumeration across all reset scenarios. Another angle of the conformance is, our NVMe products must implement and conform to the PCI system bus register specifications. And ensuring full compliance, it's essential for interoperability and certification. So the impact, no fatal errors, but of course, non-compliance can lead to subtle integration issues or certification delays. IOL automated tests, they validated the NVMe tech specific portions of the PCI system bus registers, and it helped ensure the adherence to the spec and a good integration with host platforms. And yeah, so the NVMe based conformance, this is the validation of admin and NVM command subsets for complete functional coverage. The problem could be, basic commands, they appear to execute without errors, but a complete validation is required to confirm robustness. So not much of an impact as such, but yeah, we shouldn't get unexpected command timeouts or errors. The IOL automated tests validated the core NVMe device functionalities, which were implemented in the hardware and the firmware. And because of this, we were able to ensure, again, reliable execution of standard commands across platforms. Continuing for the base conformance, the validation of key system memory structures, such as physical base address offset, completion queue, entry, status field, generic command status. So the problem, it's the same, that we want to ensure the hardware and the firmware, they strictly follow the NVMe spec. If there is any deviation from these structures, there is a possibility of unexpected results or inconsistent behavior. So IOL tests verified that all relevant system memory structures conform to the NVMe spec, and this in turn helped us ensure a better system behavior across different platforms. Yeah, thank you.
Thanks, Rish. Yeah.
Hi, everybody. Let me present as well Xinnor view on the problems that we are discussing today. So, 2 words about Xinnor. We exist on the market only by the reason that NVMe provides great performance. But in case if you try to couple many NVMe drives, and in case if you need to have data protection, then you don't have a chance to get such great performance if you use standard array technologies that were applicable for previous media generation. What we do? we do software rate for local drives as well as erasure coding for disaggregated drives. We support different erasure coding levels. It means that it could be rate 5, 6, even n plus m, where m could be up to 32 drives for parity. As well, we support, as I told, local drives connected to your host machine, or we support as well disaggregated drives all over the network. We have basically two versions of our software, one in kernel space and one in the user space. These two versions covers different use cases. Kernel space version, it's more foundation for file system, especially parallel file system on top of our solution. User space version, it's more related NVMe over Fabric use cases. So the question of today's webinar is how compliance testing for the drives could be related for the rate or erasure coding when you join different drives in one array. So let's discuss this in a bit more details. But prior to that, let's look on the industrial use cases where such data protection matters. Especially, it matters now for HPC and AI workloads, where the main task is that GPU shouldn't be idle. Therefore, all data storage could be could provide minimal delay and minimal idle time for the GPUs. So let's go on more specific use cases. First use case I would like to cover today related to the silent data corruption. So what would be in case if the drive doesn't report properly that we have an error related to the silent data corruption? This case, we have problems in two use cases. First use case related to the RAID rebuild. In case if we have silent data corruption in the drive, and after that we have different drive failure, then what we have typically wrong parity. And when we try to rebuild failed drives, then we get to the failed data what is absolutely critical. It's for rebuild. The same problem related to the read modify write. In case of read modify write, in case if we have silent data corruption problem with the drive, when we do on this stripe read modify write, we have wrong parity. And in case if we will do rebuild, then we will have wrong data, failed data on the drive that would be rebuilt. So what could be a solution for this problem? The obvious solution for this problem is error injection tests of the drives that were mentioned by Nolan. So the drive could properly report to us silent data corruption problems, and this case we wouldn't have such problems on a RAID level. Let's go further. Let's consider a bit more different use case related to the drive streams. Why this use case matters? Because today in a lot of installations, typical drives that are used are read-intensive drives. And this case trim from the application or from the file system extremely important in case that application would have sustainable write performance. So what would be in case if we would have a drive which wouldn't call back to us zero, that would not call back to us zero after trim. Let's look in the picture. And let's assume that drive, which is mentioned DN, doesn't provide to us, doesn't return to us 0 after trim command. This case, if we will do trim for the not whole stripe, for example, we will do trim from the file system starting from the D1 drives. Then in case if drive DN wouldn't return 0 after trim, then we would again will have a wrong parity for the all stripe. And during rebuild process, we would have absolutely same problem that we would have in case of silent data corruption operation. So what is important? It's important that all the drives should be compliant to the trim standards, and they should provide zeros in case trim operations comes to the drive. Okay, so the next problem that I would like to address after we can see the trim, let's look on the problem related to the different queue latencies that could be provided to the drives. All of us know that RAID typically is working with the performance or with the speed of the less performant drive. So this case, let's assume that we have all the drives that have several milliseconds latency, and we have one drive with 500 milliseconds delay or 500 milliseconds latency. This case, all the RAID will have the latency of the drive with a 500 millisecond delay. And it means that you can forget about all the performance you can get out of this RAID array. So this case, what could be a solution of this problem? It's as well should be testing of the drives that they should provide the same latency or the same range of the latency in different workloads. Nolan, could I ask you to move to the next slide? Okay, thank you. Solution of this problem is more or less the same as a solution for the problem which is called saturation tests. This case, we don't have a problem with the latency, but we have a problems that different drives provides different SLA, say provide different IOPS or different bandwidths related to the gigabytes per second. This case, we have absolutely the same problem. RAID is working with the performance of the less performant drive. And this case, we have a problem that we cannot get performance of the overall storage, which could be expected. Could we go to the next slide? Next two slides would be more related not to the data path of the RAID engine or erasure coding that we discussed before. They are much more related to the control plane and which is related to the drive functions and as well RAID functions. Let's assume that drive detects an internal correctable error. This case, RAID controller requests smart health monitoring information to assess the drive health. Let's assume what would be in case if the drive will provide to us incomplete or improper information, or differently reports a critical failure in case of the non-critical events. Event. Basically, we would have here two different types of the problems. First type of the problem are related to the no predictive failures. This case, controller cannot predict an impending drive failure to begin migrating data proactively. Totally opposite situation could be in case which is called premature drive failure. This case, controller may mark a perfectly healthy drive, which is absolutely fine, absolutely okay, as a failed based on false data and initiate rebuild. Both situations equally worse for RAID, and both situations connected with very simple root cause that drive doesn't support proper error handling mechanisms and doesn't call back proper attributes on smart monitoring. What is as well highlighted by Carter in his presentation. And Nolan, could I ask you to switch to the last slide? And the last case related to the hot plug, hot swap failures, because all the erasure coding technologies now use such mechanisms that supports immediate back-in to the RAID hot pluggable, hot swappable drives. The problem is that non-compliant drive doesn't adhere to strict hot plug protocols. It could create a power surge on the bus upon insertion, affecting adjacent drives, or it could initialize improperly on the PCIe bus, causing the bus to reset. Both situations equally very bad. This case, the catastrophe is that we could see the collapse of the overall bus, and it means that we can lose all the data of the RAID independently on the case which RAID level protection is supported by RAID. Because this case, if we have bus failure, bus collapse, then this case we will lose all the drives in RAID engine. And as well, the remedy is compliance testing, which will validate all the drives in terms of proper implementation of hot plug and hot swap failures. Okay, so we look today on just several use cases. I will be very pleased to answer on all the questions, not only related to the such use cases. Thanks, everybody.
Great. Thank you, Dmitry. Now we'll go ahead and dive into the Q&A. Please share any questions you may have into the questions box for our speakers. So our first question for today is for Carter. How has IOL Interact evolved over the past 13 years?
Yeah, so at the very beginning, there wasn't as much driver support for IOL Interact or just NVMe in general and Linux. So I think originally there was NVMe from Intel when they were first coming out then. So we bootstrapped a lot of that then from Intel, from open source NVMe and NVMe. But since then, the Linux kernel and default driver has caught up a long way. And where there are limitations on the Linux kernel driver, the IOL has their own user space driver to step in, so to give us a little bit more granularity and control. So the main ways it's changed is we don't have to rely on the old Intel driver. The Linux kernel driver has caught up and gives us a lot of control, and where we have gaps, we can use our own user space driver. And then just the tests, there's been like additional command sets added to the test software, additional transports added to the software. So it's just expanded and gotten more control over the years.
So our next question is, how does UNH-IOL balance vendor neutrality with collaborative testing?
Yeah, so the collaborative part of the program really is primarily about how all the feedback and updates from the test plans from multiple member companies all get combined into the next version of the test plan. So the collaboration is just through efforts of all the testing going on over the previous 6 months. We're not directly sharing any feedback or anything with other member companies other than in the form of test plan updates if there's like an error in the test plan that one particular member company points out or something like that. In the event of a PlugFest event, member companies will work directly with each other, plugging their devices into each other's devices and making sure that there's no interoperability issues between the two of them, in which case the neutrality it benefits both of them in that case.
Excellent. Our next question is also for Carter. How are test plans approved before being adopted?
Yeah, I talked about this a little bit in the slideshow. Just like any other NVMe technical proposal or new feature, the test plans go through the exact same review process. So they go through from a phased approach, a 7-day member review to make sure we've got like the right features identified for newer compliance requirements. And then it goes all the way through until we develop the whole test plan and then submit that to the NVMe technical work group for 30-day member review. And then after that completes, and as long as there are no questions being raised or major red flags that would block it otherwise, it goes to the board for ratification. So just like any other feature in NVMe, the test plans go to the board for final approval.
Excellent. And then one last question, looks like for you, Carter. What are the criteria for a device to be listed?
Yeah, there's a handful of requirements depending on the device. The most common device we get for testing is a PCIe SSD. So there's an array of test plans for that device, which is the NVMe base and NVM command set test plans, as well as PCIe transport testing and PCIe interoperability. So passing all the mandatory tests in all those test plans are required. If the device is over a different transport, say it's a NVMe target or a JBOF or something like that, then the requirements are a little bit different because we'll do different transport-specific tests and configurations. But at the end of the day, looking at the test plan, if there's a mandatory flag next to that test for that provided transport or implementation, then that is the requirement to get put on the integrators list.
Excellent. Looks like that was our last question for today's webinar. So I wanted to say thank you to our speakers and thank you for everyone for joining. If you'd like, the webinar video will be available to download, to view on BrightTalk, as well as the NVM Express YouTube channel, and the slides will be available to download on the NVM Express website. Thank you everyone for joining.